Here is a problem where the joint density function of x and y is given. So the joint density function is 1 over x squared y squared, where x is greater than 1, y is greater than 1. So it's the density function is only valid here. And we are given two functions, z is x plus y, w is x minus y. The problem is to find out the joint density functions, marginals, and so on. All right, so let's see how to do this. First, we solve for the roots and see what the region where this the new density function will be valid. So from here, this is two linear functions. So if you solve for x1, we can do it mentally. That's z plus w by 2, and y1 is z minus w by 2. So that's easy, the solutions from here and here. But notice that x is greater than 1, y is greater than 1. So x plus y, of course, will be greater than 2. So that's one condition on z. And w, notice that it's x minus y. Because of the minus sign, this could be larger than this. So we see that there's a w could go from minus infinity to plus infinity. But this is telling us more. From here, this is x1. x1 is greater than 1. So we get additional condition that z plus w is greater than 2. And similarly, y1 is greater than 1 because it's given. So from here you get z minus w also is greater than 2. So we get these two additional conditions on top of this general observations. So we need to put all this to figure out the region of integration, or the region where the new joint density function is non-zero. So the question is, where is this non-zero? So this can only be non-zero over this region because this gets translated into this. So let me draw that, and then we will go from there. So first the condition is z is greater than 2. So this is, let's say, zw. This is the 2 point. And then we had z plus minus w equal to greater than 2. So let's do the lines z plus w equal to 2 and z minus w equal to 2. So if you take, so it's going to be a line passing through z at 2, because when w equal to 0, z is 2. So one line would look like this. So this would be z minus w equal to 2, because so this is z minus w equal to 2, because when z is 0, w is minus 2, and the other line would go like this. So this is z plus w equal to 2, because when w is 0, z is 2, and when z is 0, w is z is 0, w is 2, and w is 0, z is 2. And so for us, it's the region beyond this. This is where z plus w, z is greater than 2 minus w, or 2 plus w. So it's this region where the density function is non-zero. So if z, the joint density function z and 0, z and w is non-zero, is not equal to 0 in this region, when z comma w belongs to this shaded region D. All right, now to figure this out, we need to find the Jacobian. So that's the second step. So Jacobian is dc by dx, dc by dy, dw by dx, dw by dy. So these are easy because it's linear. It's 1, 1, 1, minus 1. So that's the Jacobian is minus 2. 1, minus 1, minus 1, minus 2. So the absolute value of the Jacobian is just 2. So we are actually ready to find the joint density function c comma w is 1 over the Jacobian, done in this manner, and fxy x x1 comma y1. So if I substitute, this is going to be 1 over z plus w by 2 multiplied by z minus w by 2. That's x1 y1 squared. So this is 4 squared is 16, cancels with 2. So this turns out to be 8 over c squared minus w squared, the whole squared. And we bring in all these conditions that we derived before. Uh, c is greater than 2, and but in fact more. C plus w is greater than 2 and c minus w is greater than 2. So we can write that together as, and that's really this region. So that's the answer for, and it is 0 otherwise. Notice that w does go between minus infinity to plus infinity, but in this conditioned manner. So all right, so as far as the joint density function is concerned, that's the, so notice that not only c is greater than w, c is beyond, c plus minus w is beyond the 2. So if you want to find out z, we integrate over w, so over this region. So here w goes to z minus 2, and here w is 2 minus z, but z is greater than 2, so I'm going to write it as minus z minus 2. So it's a symmetric region. And so we'll integrate w over here. And later, when to find out w, we integrate over this region, depending on whether w is positive or negative. So let me go ahead and do the integration of FCC. So that's minus z by 2 to z by 2, c by 2 FCW, c comma w dw. So that's going to be minus z by 2 to z by 2, c minus 2 to 8 over c squared minus w squared, the whole squared, dw. And remember, w is the variable of integration. This is an even function, so we can write it as 2 times the integral from 0 to infinity, 0 to z minus 2. So 2 and 8 gives you 16, and z squared minus w squared, the whole squared. The question is, how do you integrate this? So I'm going to, many ways you can do this. I'm going to do a partial fraction. It's easy to show a partial fraction here. So notice that the inside you can write it as z plus w multiplied by z minus w, the whole squared. I'll tag up this constant later, but this gives us ideas. So this we can write it as 1 over 2z over z plus w plus z minus w, the whole squared. Because this gives you 2c. The reason I brought 2c is here, that's not the variable of integration. So when I expand that, I get 4z squared, 1 over z plus w, the whole squared, plus 1 over z minus w, the whole squared, plus 2 divided by z plus w and z minus w. So I'm going to do the same thing on this one more time. Notice that this itself I can write it as 2 divided by 2z 1 over z plus w plus 1 over z minus w, because c plus w, c minus w, 2c. So 2 cancels, and let me write all that here. 1 over 4c squared, 1 over c plus w, the whole squared, plus z minus w, the whole squared, plus 1 over z. So here this is easy to integrate each term because it's either linear or quadratic, so it's quite easy. So if you want to integrate here 0 to z minus 2, we just integrate everywhere, 0 to z minus 2, 0 to z minus 2. I just have to concentrate on the last thing. Remember, integration is with respect to dw, like here. I'll bring in the 16 a bit later. So let me do the integration term by term on the other side. So we have the integral from 0 to c minus 2 1 over c squared minus w squared the whole squared. So I'm just going to do it mentally. I pull out the constant outside. Then I have, so the integral of this is, you can see it is z. Remember, the integration is with respect to w. So if you differentiate this, you get this term, because the minus 2 plus 1 divided by the minus 2 plus 1 is minus 1, new exponent. So divided by that, you get the minus 1, and because of minus 1, it comes in the denominator. Here it's going to be 1 over z minus w, but with the sign change, because if you integrate, if you differentiate this again, you'll get this, because it's minus minus twice, right? Differential of this is 1 over c minus w the whole squared multiplied by the minus 1 multiplied by another minus 1 because of the derivative of w. So you get this plus 1 over z. And here you can see this is log of z plus w. And this is log of minus log z minus w. Because when I take the derivative of this, I get 1 over z minus w multiplied by minus 1. So you get back that. And this I can, so I'm going to, before I substitute the limits, let me rewrite this as 1 over 4c squared log of z plus w over z minus w, because of the minus sign here. 0 to z minus 2. All right, so if you want FCC, all you have to do is multiply by 16, right? Because FCC is here, so I'm going to multiply by 16. 16 here, 16 here, so 4 and 16 cancels off. So let's substitute the limits. The bottom limits are easy, so I'm going to do that first. So notice when w equal to 0, I get minus 1 over. So there is no square here. The square is minus 2. After integration, you get just the linear terms, 1 over the linear term. So when I substitute the lower limit 0, this is minus 1 over c, this is plus 1 over c, so these two cancel. Here w equal to 0, you get log 1, 0. So there is no contribution due to this. So the top limit is going to be, let's do this carefully. So I'm going to substitute w equal to z minus 2. So the top limit minus z minus 2. So this comes out to be like this, plus the top limit is z minus 2. C cancels, so you get 1 over 2 plus 1 over z log of z minus 2. So that is 2 multiplied by z minus 1. Here z minus 2, here just 2 cancel, so it's z minus 1. And z is of course greater than or equal to 2 from the original one. And if I simplify all this stuff, so first of all, I'm going to do a little bit cancellation. I'm going to take the 4 inside, or rather a 2 inside. So I'm going to have 2 over z squared. Then I have here 2 cancels. So this becomes 1 over 1 minus 1 over z minus 1. Plus 2 over z log z minus 1. So let me see. So this, if I simplify, this becomes z minus 2 over z minus 1. So the whole thing can be written as 2 multiplied by z minus 2 divided by z squared z minus 1 plus, so I'm pulling the z squared outside. Here we have 2 over z cubed log z minus 1 for z greater than 2. So notice that at least for z greater than 2, everything is positive, and consequently, at least the positive thing is, so just to verify, we'll check whether the area under this is 1. So this is the answer we are getting for x plus y. So the area is z. Remember, z goes from 2 to infinity. FZC is integral 2 times 2 to infinity z minus 2 over z squared z minus 1 plus 2 over z cubed log z minus 1 dz. So I'm going to split this into two terms as before. So this is 1 over z squared minus 1 over z squared multiplied by z minus 1. You can see, write this as write the numerator as z minus 1 minus 1. So z minus 1 cancels 1 over z squared minus this. So if you want, you can write this as 2 to infinity 1 over z squared dz minus integral 2 to infinity this mess z squared. So this we can do by partial fractions, but we may not have to. Let me integrate this part also. So this we can do by part. This is 2. So if this is du, u is going to be minus 2 multiplied by z squared multiplied by log of z minus 1, 2 to infinity, plus one more term, minus. So notice that 2 cancels. You had a minus 1 before. Then integral 1 over z squared from here, and the derivative of this, which is z minus 1 dz, 2 to infinity. So minus minus becomes plus. Notice that this term is exactly the same as this with a minus sign, so this goes away. The derivative of this is 2 multiplied by minus 1 over z 2 to infinity. And when you come here, when you substitute the top limit, this rapidly goes to 0. So the top limit is 0, bottom limit is z equal to 2. Here it is finite. log 1 0. So this term also has no contribution, but this is just half. So this is 2 over 2, this is 1. So that checks. So the density function once again is 2 multiplied by z minus 2 over z squared multiplied by z minus 1 plus 2 over z cubed log z minus 1 for z greater than equal to 2. So that was the marginal density function. And somewhere before we had the joint density function as this one. So now I'm going to do the the W, the PD, the marginal density function of W. So once again, W is we have two cases to deal with. So when W is positive, you integrate in this region. When W is integrate, C goes from, so C goes from 2 plus W or 2 minus W. So this is going to be, so C goes from, remember, Z is going to be integrated out. C goes from, when W is positive, C goes from 2 plus W to infinity. Otherwise here, W goes to, Z goes to 2 minus W to infinity. Both are positive. Obviously, 2 plus W is positive, 2 minus W is positive. And the joint density function is, I'll write it here, 8 over Z squared minus W squared, the whole squared, dz in this case. So because I'm going to take the derivative of this, so again I'm going to rewrite this, except that because I'm going to take the derivative of this with respect to z, I'm going to rewrite in a slightly different form. Remember, previously we wanted to bring out 2z here because we were doing the derivative with respect to w. Now we are doing the derivative, so I want this to be constant as far as the difference, the integration is concerned. So this is going to be 1 over 4w squared, 1 over z minus w the whole squared, plus 1 over z minus w, z plus w, z minus w. And the next term is minus 2 times the product of these two. So I'll write one more line, c minus w multiplied by c plus w. So which I am going to rewrite this as once again I'll bring up the 2w downstairs, so that this is now reads 1 over z minus w minus 1 over z plus w. Z plus w, z cancels, and 2w cancels, 2 cancels, so you get this term. So we will just integrate this from, so remember, integration is with respect to dz. So we'll integrate and then put the proper limit. So once you integrate, you get 4w squared so remember the integration is with respect to z, so this comes out to be 1 over z minus w with a minus sign. Same thing here, z plus w with a minus sign, and then minus 1 over w. Integration is with respect to z. So you get this is log of z minus w minus log of z plus w. So I'm just going to write this as with the proper limit. So which I'm going to carry over the next page. So what we are interested, f w is so now we can, there is a constant 8 so, and 4, so that becomes 2 over w squared multiplied by, so I'm just going to repeat this because this needs to be in order to avoid confusion. So this whole thing goes from w plus 2 to infinity, 2 plus w to infinity. Similarly, the same thing two minus w to infinity. So if you do this, I guess you can just do it at, yourself. And let me write down the what I get here. So with the w squared, this becomes w cubed. So this is for w positive, and for w negative, we get so that's FWW. The question is this right? So we can actually do a check, which is, so let me do one side, then you can see what I'm doing and do the other side. So I'm going to show that it's actually symmetric, you can see, because if you want, you can write this as you can do that because minus w here is plus, so you can write this in this manner. So that's for w between minus infinity to plus infinity. So to see whether the area under this is 1, I'm going to just do this top part and show that area is half, I believe. So let's see from 0 to infinity FWW. So that we need to integrate 0 to infinity the top term, 1 over w squared multiplied by 1 plus w dw plus 0 to infinity 1 over w squared dw So there's already problem here, because if you do this directly, this is going to blow minus 1 over W, and top limit is fine, but bottom limit seems to have issues. But let's not, let's see what the other terms are. Minus integral 0 to infinity 2 over W cubed log of 1 plus W dw. So this is going to be, so let's integrate this. So this is the first term. I'm hoping it will cancel out like the other one. So I'm going to save this. And here it's minus 1 over W, 0 to infinity. So that's an issue, but let's keep going. Minus from here, 2 log of 1 plus W. Derivative is minus 2W squared. And this need to evaluate at 0 to infinity. Right? I took the derivative of 1 over omega 3 W, that's minus 2 W to the power minus 2, which is here. And the last term is, so minus minus becomes 2 cancels. So the last term is going to be minus integral 0 to infinity 1 over omega squared will stay, and the derivative of this, that's 1 over omega W squared multiplied by 1 plus W dw. So the interesting thing is this term and this term cancels. So we just have to deal with this same limit. So I'm going to couple them. And so this reads now 1 over W minus plus minus minus plus 2 cancels, log of 1 plus W over W squared, 0 to infinity, which I can write it as minus omega plus log 1 plus W over W squared, 0 to infinity. If I put infinity, this will be of the form infinity over infinity here. If I put 0, this will be log 1 is 0, 0 over 0. So both the limits are indeterminate. So I'm going to use the L'Hospital's rule and then substitute which I will have to do for both. I'm just going to, L'Hospital's rule is take the derivative of the numerator and denominator separately and then substitute the limit. So minus 1 plus 1 over 1 plus W, the derivative of the numerator. Here it is 2W. And if I couple this, this becomes minus 1 minus W plus 1 over 2W 1 plus W. Remember, the limits are 0 to infinity, 0 to infinity. So 1 cancels, then you have minus omega over 2 omega W plus 1, 0 to infinity. So W also cancels. So you get minus 1 over 1 plus W, 0 to infinity. So when you put the top limit, this goes to 0, and minus minus goes away. When there is a 2 here. When you put the bottom limit, you get half. All right, so the area under the first half is 1 half. So the area under the other half is exactly the same, a half, and so the whole area turns out to be the 1. Checking that this is a proper density function. And you can see this is a complicated function of W, and same thing we had before, some other function of Z, a messy function for the density function of Z. And if you take this product, this is not going to equal this neat function. So we conclude that they are not independent. They are dependent random variables. So this is the complete solution of this problem.